Welcome back to most of you. How many first-timers here, if you can raise your hand? We've been doing this for 14 years, and this is your first time you figured this out. Welcome, one and all. This is the first time that we actually have a triple sellout. You're apparently the lucky ones to get the main venue. There's spillover into our next largest room, and then spillover into the next one. And not only that, we are live streaming on the internet, so a lot of people will participate in this 14th annual Isaac Asimov Memorial Debate. I want to publicly thank Janet Asimov, Isaac Asimov's widow. Those of you who might not know, Isaac Asimov he wrote more than 300 books, and much of the research that went into his nonfiction books, and perhaps some of his fiction books, was conducted in the research libraries of this institution. And so there's a connection that we have with him that few other institutions had. And his family decided that we would conduct this annually in his honor. Isaac Asimov, perhaps the last polymath of our civilization. So I want to publicly thank and acknowledge Janet Asimov on that. Tonight's subject, as you have surely gleaned by now, is nothing. And the existence of nothing. And the program, just so you know, we weren't running out of toner, all right? We were trying to figure out a way to have the title become nothing. So this is our attempt to capture that fact. There's nothing wrong with your program. Since we last met, an asteroid struck Russia, the Curiosity rover plunked down on Mars, the Higgs boson was discovered. The universe has been a busy place. A lot does happen in a year, and it's just great to have all of you back each year. The subject of nothing. I don't know if George Gershwin wrote the first song ever on the subject of nothing, but in Porgy and Bess, the title of the song was, "I've got plenty of nothing, and nothing's got plenty of me." And so nothing, of course, has been on people's minds a long time. Actually, back then, the words of that song would have been uttered, "I got plenty o' nuttin'." That's how they were written. Times have changed, haven't they? My parents are here this evening. They're 85 and 84 years old. I just want to publicly recognize them. They brought me here as a child at age 9, my first visit to the Hayden Planetarium here as a native of the city. And today, I am the Frederick P. Rose Director of the same place that launched me on this epic voyage of discovery. So those are institutions operating at their best. They brought a friend with them, Heidi Sweets is her name, and they forwarded me a poem she wrote on nothing. I felt compelled to read this before we begin, to set some of the mood of the evening. Nothing speaks volumes. Imprisoned dreams, jailed forever, forgiveness weeps. No tears are released. Silence begs for ease. Anger has no hope. Indifference rejoices, while nothing holds court with jesters of time. Nothing waits and waits. Thank you, Heidi, for that contribution. Written before she even knew of this panel. Let's bring out our guest and get the party started. My first guest is a professor of physics at Stanford University, professor of theoretical physics, that is. Don't know if she's ever even visited a particle accelerator, but she tells him perhaps what to look for. Professor Eva Silverstein. Eva. Next, we have our first time ever three-peat three-peat. We have the physicist and professor of Earth and space exploration, Lawrence Krauss. Lawrence, come on out. Lawrence was in the first ever Asimov debate. The fact that he's been here 3 times means he just always works on controversial topics. Hence, we always reach for him. My next guest, a longtime colleague of mine during my days at Princeton, is J. Richard Gott III. He's professor of astrophysics there. Rich Gott, come on out. Rich, you brought a shopping bag. I don't know what you got going there. Maybe we'll find out later. I'm almost afraid to ask. Reminding you that this is a debate about nothing. So, next, we have a longtime writer, contributor to major publications, and his specialty on the topics on which he writes is the intersection between physics and philosophy, Jim Holt. Jim Holt, come on out. Thank you. And last, and I was going to say not least, but it kind of is least because this guy is the world's expert on zero. Charles SIFE, come on out. He's professor of journalism, New York University. So the way this works is you are eavesdropping on a conversation the 5 of them will be having that I will be steering. All right, these aren't lectures, these are not, it's kind of just see what we would talk about if we were at a bar. That's really how this works. We've done this 14 years in a row, and we have a fun time doing it, and I'm glad you're here to join us. So each of the 5 panelists will start out with like 1 or 2 minute remarks, just so you can hear their voice and get a feeling for how they speak, and then we'll jump right in. So Eva, please, let's begin with you.
So let me just say that one of the greatest results in all of physics, I think, is our understanding of how structure in the universe formed, starting from quantum fields that for all practical purposes were in their ground state, in their vacuum state. And that, combined with the inflationary expansion of the early universe and quantum mechanics, leads to the origin of structure that we see today. And just last point about this for now is that one of the most interesting features that we've learned about this more recently is its sensitivity to very high energy physics, questions that bring in problems of quantum gravity, and which on the one hand, and which on the other hand are accessible through some observations of the microwave background radiation. So to me that's the most interesting version of nothing that I know.
So you're saying when you say it's sensitive too, you mean possibly experiments can come and have a bearing on your theoretical meanderings? Indeed.
So the inflationary theory is subject to probes. In fact, there's one coming out tomorrow that's very relevant.
Tomorrow, so we're one day too early. But we did get to hold today on the vernal equinox, right? Just so you know. Happy spring to everyone. And those of you on the internet, if you are the 15% of the world's population who lives south of the equator, happy autumn. Okay. And that would include 100% of the world's penguins. Happy autumn to penguins. Free penguins, that would be. Lawrence, please reintroduce yourself to everybody here. Thanks for coming. Just off the plane from Sweden, by the way. Lawrence, thanks for coming in a third time.
It's always a pleasure to be back and to have fun here. Well, obviously, I've thought a lot about nothing. I've written a book about it recently, but I think that the most exciting thing, there are 2 things. First of all, that we've learned that most of the universe is nothing. Nothing is the most important part of the universe, so you're all more insignificant than you thought. And the second thing is that if you asked, and one of the things I find most amazing is if you asked what would be the characteristics of a universe that was created from nothing by just natural laws without any supernatural shenanigans, it would be the characteristics of the universe we live in. And that I find amazing and worth celebrating, because it makes God more redundant than God was before. And the other thing I guess I want to say before I end is I think Jim, who I greatly admire, I expect will disagree with some of the things I want to say. So I want to say right off at the beginning but for those people who are old enough and understand the spirit of what I'm about to say is...
Well, you
Jim,
want to
you're
start
an
a fight already.
Well,
These
hold
are
on,
just opening
just
remarks.
Neil, let me finish what I'm going to say before you interrupt. You'll interrupt later. So I just want to say, Jim, you're an ignorant slut. Okay.
For those born before 1960, that's an expression on Saturday Night Live uttered in
Exactly. I didn't mean
1975.
anything.
Yes. Next, Rich Gott.
That's how it's going to go. I'm Rich Gott. I work on general relativity and cosmology, and I discovered an exact solution to Einstein's field equations for a cosmic string and for then two moving cosmic strings. And that was interesting because it allowed time travel to the past, like several solutions that are known. Kurt Gödel found one in 1949, and then there's the wormhole solution. I'm wearing a coat tonight that Bob Kirshner called the coat of the future. He said, Richard, you must have gotten this coat in the future and brought it back in your time machine because this color hasn't been invented yet. So whenever I'm talking about time travel, which I will a little bit tonight, I wear this coat. So I'm relevant to tonight. Li-Jing Li and I worked on a quantum vacuum state that we thought might be relevant for the creation of the universe. We'll say more about that.
Okay, excellent. Thank you. Jim Holt, what have you got for us?
In the light of Lawrence's, or may I call you Larry, your ungallant allusion to me, I am not ignorant. I'm going to spend most of my breath attacking you, and I'm going to attack you from the left. You are an avowed militant tub-thumping atheist, and the old equation that we have that we inherited from Christian metaphysics is that God created the world out of nothing, so it's God plus nothing equals the world. And you take God out of the equation, and I'm all for that, but so now we have blank plus nothing equals the world. And what you put in the blank is the laws of nature, the laws of quantum field theory. And I think that actually in worrying too much about the problem of why there's something rather than nothing and trying to find something to put in the blank where God used to be, you're actually still in thrall to Christian metaphysics. And I think you see the laws of nature, particularly the laws of quantum field theory, very much as divine commands. So I think you're shall we say, insufficiently enlightened.
Oh,
How dare you
snap!
be so rude? Why, no one's ever said that.
We'll revisit this. So, Charles, Mr. Zero.
I don't know how I'm going to follow this.
Wait, we get his microphone working over there?
Hello, testing.
They turned it to 0, I think.
You are so full of zero. Why don't you borrow this?
I'm Charles SIFE, and I think I'm just here to fulfill my father's prophecy that I'm good for nothing. I was born to be a mathematician and didn't wind up that way after studying mathematics for a while. I wound up in the Economist building in London and realizing that, hey, journalism is a lot more fun than sitting in your office doing the silly of not invariance. So I joined the circus, became a journalist, but of course my mathematics core was still there, and my first book was about math that I loved, and perhaps the most fascinating thing I encountered during my studies was zero.
Cool. So I'd like to start with you. Test your mic one more time. Is it?
Testing 1, 2, 3.
Yeah, he works now. Good, thank you. So I just want to start out with you. Zero, it seems to me that was that people's first attempt to quantify nothing, to turn nothing into something? Because, of course, in case you never noticed, Roman numerals cannot represent zero. You ever thought about that? There is no zero in Roman numerals. So ancient Rome and their huge and great civilizations precedes the invention of zero. Is that right?
That's absolutely
That's
correct.
right. So what took so long?
Well, we humans had a real revulsion for nothing, for void, for
Don't we
emptiness.
still? Was it then and not now?
Oh, it's still here. It's still here, although it's diminished somewhat. I think it's because, in part, we humans have.
I think that's what you said. We humans.
We humans.
Okay.
Am I including people that I shouldn't?
No. Okay. No, we're good. We humans, go. I just like the phrase. Go.
For us, nothingness represents something that we're afraid of, that disorder, a breaking of the rules. That one of the things that we humans do is we control our environment. And the way we control our environment is through imposing order on things, by figuring out the way things work. And zero represents, in some ways, nothingness represents a return to the lawlessness, the primordial ooze without rules. For example, if you look in the Bible, the Hebrew Bible, the creation myth starts...
It's the Old Testament to Christians, okay? Just so you get the... Go.
The creation was out of nothing. If you read the Hebrew, it says the world, the earth, was formless, chaotic, and void. And it's not a coincidence that chaos and void were twinned, because the void represented a lawlessness, a breaking of the rules, that how could something which was nothing have any rules that defines what it is, how it works, how it behaves? And by breaking the rules, it became scary.
But the primordial chaos was not nothing. It was a disordered something. I mean, the Hebrews...
I got to go with Jim on this.
The ancient Greeks didn't really have a concept of absolute nothingness. They thought of the things began in chaos, and order was imposed in chaos, and chaos became cosmos. But it was only with Christianity, I think, that the idea of creation ex nihilo came to
Out of
be
nothing.
formulated. Yeah.
Okay.
Because
Translating.
the idea was that God was so powerful, was so all-powerful, he didn't need any pre-existing material to create the world.
In fact, it actually comes from way before the Greeks, the Rig Veda. All of it didn't have creation from nothing. It was creation from some primordial stuff.
Yeah.
Often water in a lot of the creation myths, but primordial stuff.
Yeah.
As opposed to the real nothing, which is what I'm going to talk about.
By the way, the Hebrew term for that in the Bible is wonderful. It's tohu bohu, which...
And actually the tohu is the chaos.
Okay. So
Chaos.
what's the
And
bohu?
bohu is actually a very difficult word in Hebrew because it was used, I believe, 3 times in the Bible. And it is believed to mean void.
Okay.
In the true sense. I mean, it may not have been exactly...
Well, that's
what
why, because today when anyone uses the word chaos, we're not referring to a place where nothing is happening. We're referring to a place where everything is going on, but just in a disordered state. So the modern use of the word chaos is not consistent with nothing, I would say.
But that's the whole point, I think, is that the ideas of nothing have changed since these vague, ill-defined notions, and that's good. It's not a bad thing. It's called learning.
Well, however, but in the Hebrew Bible, we presume, regardless of whether there was are we saying the void and the chaos preceded the formation of the universe, or is that just the early universe as described in the book?
Well, it's actually ambiguous because if you looked at, say, the Septuagint, one of the versions of the Bible, that in fact there's an implication that there was a previous creation and that there was a creation out of nothing, the chaos of the previous creation. But in the Bible that we use, the Pentateuch, it is the use of the past implies that this is the first creation out of nothing.
So Jim, when did philosophers start weighing in on this?
Really with Leibniz in the 17th century. He was the first thinker to pose the question, why is there something rather than nothing? And by nothing, he meant a state in which there are no existence at all. There are no entities, there's no chaos, there's no space, no time, absolute nothingness. It's very difficult to grasp in the imagination. If you try to obliterate all of the contents of your consciousness or try to imagine all of the contents of the universe slowly being extinguished, the stars going out, the atoms disappearing, life disappearing, time and space disappearing. It's interesting, the son of Samuel Taylor Coleridge, Hartley Coleridge, as a child, had precisely this intellectual struggle, and he said, and I imagined, all of this disappearing, all the grass and the stars and the people, and there was nothing but dark and cold, and nothing to be dark and cold. So that, that's the best you can do, and even when you try to reach nothingness in your imagination, there's still, the little light of your consciousness, creeping under the door. The only times I've succeeded in imagining absolute nothingness is 2 times. Once
But
during,
you've succeeded. at
yes,
this.
once during
Under what
actually
influence?
every night during dreamless sleep, and once while I was watching professional bowling on television.
Okay. Not a bowler, I would guess here. Okay. Leibniz, but just I give
Leibniz.
Excuse me, Leibniz. I'll give you space to hypothesize here. Would you say that his thoughts of nothing contributed to his invention of the calculus, or put him in a place where, because Leibniz as well as Newton, sort of co-separate inventors of calculus, almost contemporaneous. So, do you think one of those had to do with the other?
Yeah, well, the crucial notion of the calculus is the notion of the infinitesimal, the infinitely small. And what is the infinitesimal? It's not nothing, but it's not quite something either. It somehow mediates between finitude and nothingness. So, yeah, I think you have to have a sort of a temperamental attraction to dangerous ideas. The infinitesimal was considered to be an extremely dangerous idea, and there was a great resistance to the calculus because of it. And I think that...
No, why is it dangerous? You keep putting these terms
It's dangerous
in it.
because it sometimes it acts like a 0, and sometimes it acts like a
Why does
a
that
finite
make
number.
it? It's just weird.
Well,
It's
you
not
can divide
dangerous.
by it, which is always, if you're
But look,
dividing by
I-
0, then you get mathematical chaos.
I think that what Jim has pointed out is exactly it. Is one of the limitations of philosophy, really, is that, if you'll forgive me.
I'm a journalist,
is
not a
that-
He
philosopher.
won't forgive you,
I don't
but just
care.
keep talking.
Okay, is that you're absolutely right. There are some things that are essentially impossible to get an intuitive conception of, and that's just a limitation of the fact that we're classical human beings who didn't evolve to understand, to
Right.
intuitively understand quantum mechanics. So there's lots of things in science that are impossible to get any intuitive handle on, but that doesn't mean they don't exist.
I completely agree with you. And I think that a state of absolute nothingness, even though we can't envisage it in our minds, it's logically consistent, it's a real possibility, and there is a genuine question: why is there a universe rather than absolute nothingness?
Well, let me take that to Rich Gott here. Rich, you've done a lot of thinking about the early universe, about the expansion of the universe. You're a universe guy, you're a cosmos guy. And at some point, you had to wonder what was outside of the cosmos itself, or what birthed the cosmos. If not from nothing, then what?
Well, okay, let me go talk about what he just said. Let me try to give you an idea of 2 different kind of nothings that we're going to talk about. And since I'm a visual guy,
Wait, so there are 2 kinds of nothing.
There are 2 kinds of nothing we're going to be talking about tonight.
I'm going to talk about 3.
He's got
3.
a
You got a
third
4th
one.
over here? Sorry. All right. I didn't know this. All right. We have more than one nothing. All right, Rich, put up your 2 nothings. We'll look at them.
Okay, well, you take space, you get rid of the atoms, you get rid of the people in the room, you get rid of the air, you get rid of the photons that are flying around, and you get empty space, which is the vacuum. And this is what a lot of people think about when they think about nothing, big, empty, dark, we heard big, empty, dark space. That's a quantum vacuum state. And if you want to visualize that, just close your eyes. Okay? That's what it looks like. It's black, okay? It has a color, it's black. Now, that's what empty space looks like. It's alive with virtual particles and things. It has fields in it. Larry will tell you about that.
Wait, Rich, I have to interrupt for a moment. Before quantum physics was discovered and developed in the 1920s,
Yes.
your concept of no matter, no energy, no particles, no people, there was no place else to go after that.
Well, Einstein thought empty space was empty, and you had geometry. So you had Einstein's field equations where you say, here's how stuff that you're talking about, curves, space, and time. And over here you could put a 0, and then you get equations that would tell you how space and time was curved. So space and time were still there, but there was 0 energy density in there.
Okay, so quantum physics stuck energy into that the classical physics could not, or didn't know to do.
It stuck the possibility of it there. And I mean, it could be 0, and still you have interesting virtual particles and things. Physicists were quite used to thinking of a vacuum as 0 energy density, but quantum mechanics also allows you to have a non-zero energy density. And if you have a non-zero energy density, that means some energy per cubic centimeter, you have also accompanied with that a negative pressure, because the laws of special relativity tell you that if everybody who flies through this in a spaceship is going to see the same energy density, no matter what velocity they're traveling at, then you have to have a negative pressure. That's just how pressure and energy transform in special relativity. Now, positive pressure, you got that in the tires of your car. It pushes out. Negative pressure is like a suction. But we have a positive pressure in this room of 15 pounds per square inch. But
the weight of the atmosphere.
Air pressure. But we don't feel it because it's constant. It's not blowing us one way or the other because the pressure is the same all over. So in the universe, if you have this quantum vacuum state that has a positive energy and a negative pressure, it's the same all over, so you don't notice it. Except that Einstein's field equations told you that pressure gravitates as well as energy, and so that negative pressure operating in 3 directions, x, y, and z, 3 spatial dimensions, produces more gravitational repulsion than the energy does gravitational attraction. So there's an overall repulsion. So this causes space and time to expand. We've actually seen this. This got the Nobel Prize recently for the discovery of the accelerated expansion of the universe because of this quantum vacuum state, because of the repulsion of this nothing, as you might say, this quantum vacuum state, the universe is expanding faster and faster.
So that's evidence that, in fact, empty space is not nothing.
That's right.
No, it's evidence that empty space is energy, not that it's not nothing. You look, you try and find out what's there. Try and measure particles or
Right, if
radiation.
it's energy,
There's no
doesn't
stuff
not
there.
nothing include something?
Well, you know, I think you have to be a little careful. And Rich is right. The first definition of nothing, which I think is the biblical definition, is an infinite, dark, empty void. That empty void has energy, but it's still empty. There's no particles. You try and look in a region of space, take away all the particles, all the radiation. There's no stuff there, and that's nothing weighs something.
Larry, what about fields?
There are no fields. You can't measure them. There's nothing there.
It has a topology. It has a shape. It's a physical object. Empty space is a physical object. It's not.
Wait, I want to get back to that. Wait.
Rich,
you said that you take everything out of space, yet Einstein said there is still the geometry of the fabric of space-time.
Yes.
Do we have the right to say, because there is the fabric of space-time, even though it's not curved, it's just not bent by any actual matter, does that prevent us now from calling that nothing? Because we have a description for what it is as fabric of space-time.
Well, Einstein.
That's kind of what Jim's getting at, right, Jim?
Yeah.
Yeah, but that's the first kind of nothing. And then point is that's for a lot of people before physicists started talking about that kind of nothing having energy, they would have said that's a good enough definition of nothing for them, empty space. Now we know empty space is more complicated. So you might say that's not nothing. But then there's a next kind of nothing, which is no space at all. No space, no time.
Okay, so let's get back to Rich
Yeah.
on that. So I think we agree that this classical understanding of nothing has been violated by our emergent understanding of Einstein's relativity and quantum physics.
And the first person to really say this was that this is Lemaitre said that Einstein's cosmological constant was really a vacuum energy state. He said this in 1934. So he's the first one to really identify it with that. And another reason we identify that.
Lemaitre,
that
he's the Belgian priest? Is that
Absolutely.
Yeah.
And physicists.
And physicist, yeah.
He proposed a model with the Big Bang at the beginning and a coasting phase, which we don't see, and an accelerating universe at the end. So of the early people, he got a lot right. Okay. So we also know there's an early stage of the universe where we had an accelerated expansion called inflation. And what we got today is a low energy version of inflation. This is a version where the energy density in the vacuum was very high. We're talking, like 10 to the 77 grams per cubic centimeter.
That's high.
That is high.
Yes, okay.
that makes a neutron star look ethereal,
Yeah,
that is a high density. Okay.
Yeah, just
Now,
be on the same page.
Where
Okay, if you take neutron star density and make a volume the size of Thor's hammer out of it, it'll cram a herd of 300 billion elephants into that volume of Thor's hammer. So proceed.
So this is very dense. It's expanding very fast. It's doubling in size every 10 to the minus 35 seconds. And as it expands, the energy density stays the same in this vacuum state, so it makes more of itself. And another interesting thing happens. Two observers in this are separated so fast by the stretching space in between them that the light beams can't make it from here to here anymore. So event horizons occur. There's parts of the universe that you cannot see. This causes Hawking radiation. Gibbons and Hawking predicted this for this inflationary state.
The Stephen Hawking.
Stephen Hawking. He did this right after he did the black hole radiation. He said, in the universe, if you have an inflating state, you're going to have this Hawking radiation also. So if you lived back there in that nothing, you're going to see hot thermal radiation, hot Hawking radiation. It's very hot. It's 10 to the 22 Kelvin. This is very hot.
Yes, very hot. Yes.
I mean, so the tidal forces are very large. They'll tear you apart in 10 to the minus 35 seconds. The gamma rays.
Have a nice day. Yeah, right, Rich.
The gamma rays.
Rich,
will
is any
burn
good
you
news
up.
in this? Right.
But the gamma rays will burn you up, and you will. I'll tell you what it looks like for a brief instant. Well, it looks blindingly bright blue because thermal radiation, would look bright blue. So it's we could say it's a quantum vacuum state. It's nothing, but it looks violently not nothing. Okay. Now the third, or the second nothing that I would talk about.
Can I just jump in on that? Eva, you've worked a lot on. Eva, you've worked a lot on this early inflation epoch,
Sure.
very early in the universe.
Right.
And when I think of that inflation era, doesn't that come from a time where there is no structure, but then we have structure now? Is that kind of something out of a nothing scenario?
I think so. I think that's what Richard was about to get to. You start with these fields in the lowest energy state that they have. And the system is expanding rapidly, exponentially, in the way he was just describing. And that time dependence of the energy function is enough to take a system which starts in its ground state and excite it. It's not really any more complicated than that, but it's a beautiful theory of the origin of structure and testable. So.
And one of the neatest parts of it, which we don't celebrate enough, because we talk a lot, and probably you've had, I don't know if there are any of the sessions, about macroscopic quantum mechanics, which is the big thing, quantum computing. Wouldn't it be great to have quantum mechanics on macroscopic scales? The really neat thing, the most amazing miracle of inflation, is it takes quantum mechanics and turns it into us. It's quantum fluctuations that become galaxies and us. It's the most macroscopic quantum mechanics you can imagine. It is amazing, and it does it in a very simple way. It turns quantum mechanic fluctuations into density fluctuations in a simple and beautiful way. It's amazing, and we should celebrate it.
So I wanted to make one more comment about this discussion of the definition. So it's possible as a theorist to separate issues a little bit and think about turning off gravity but keeping quantum mechanics. And then you can make a very precise statement about what the ground state of a system is.
But you do this in your office? You turn off gravity?
You do this in your
turn on quantum mechanics? You just do this?
You do.
It's California.
It's California. These theorists, they're lords of the cosmos. Go on.
We don't have the budget for gravity, you know.
Go on. Turn off gravity. We have a quantum universe. Go on.
Right. I'm just trying to separate that. I'm trying to say quantum mechanics, you know, with just quantum mechanics, you can define what you mean by the vacuum state, the zero energy state. You can even consider, to be a little bit more mathematically precise, what we call a gapped system, a system for which it takes a finite energy to excite it. And I think that's also a pretty good definition of nothing. In fact, according to some of our modern theories, which relate non-gravitational physics to a dual description in terms of gravity, the two are closely related.
I'm betting that Jim Holt doesn't agree with your definition of nothing.
Well, I was going to.
You have a third nothing.
Well,
No, I have a third nothing.
Wait, just Jim, react to Eva.
Listen, the only even remotely persuasive definition of nothing I've heard from a physicist came from Alex Vilenkin, who said, you know, imagine a closed spherical space-time. Imagine the surface of a ball. It's a finite space, but it doesn't have any boundaries. Now imagine the ball shrinking down to a point. Its radius goes from finite, shrinks down to 0. So now you have a closed space-time of 0 radius. This was Alex Vilenkin's definition of nothingness. And he did some quantum mechanical computations and showed that given a closed space-time of 0 radius, there's a finite probability that a little nugget of false vacuum will spontaneously appear, will nucleate out of that, and that, by the miracle of inflation, will evolve into the world we see around us. And I think that's a really nice story. But there are two problems with it. One problem is a closed finite, a closed space-time of 0 radius, is that really nothing? Well, there's no space and there's no time, so anything that exists in space-time can't be a part of it. But what about physical laws? What about mathematical entities? What about, you know, consciousness, value, all the things that are possibly non-spatial, non-temporal? Those aren't ruled out, so it seems to me that the notion of nothingness is a very parochial
We'll get back. You raise a really important point that I want to get back to. What you're saying is you could have a universe that's got nothing in it, but if laws of physics still apply in that universe, the laws of physics are not nothing.
Yeah, where are the laws of physics?
Ava.
So this is a very interesting way to approach the problem. Take a space-time and shrink it. The problem is that general relativity, the description based on that, breaks down. Exactly. And now you need a theory that goes beyond it. There are candidates for this. The leading one is string theory, and let's talk about this briefly in string theory. 0 radius does not mean nothing in string theory. In some cases, in fact, it's equivalent to large radius for a cute reason having to do with light modes from strings winding around the small radius. But more generally, you can go where you're going instead by asking how many effective dimensions do you have? And you can ask that question by counting the density of states of the system that are available. And shrinking a space to 0 radius does not necessarily reduce the number of effective dimensions in that sense. There are processes which do that. These are processes which appear in topology changing transitions and in some resolutions of singularities in string theory. But it's a technical question that you're asking, and you can improve on that answer.
But we're all whistling in the dark here. I mean, we don't have a final theory.
Of course we don't. Of course we don't. But we still have some rules, and we try to.
Rich, let me get back to your third. Your third nothing.
Well, that's a second nothing there. The 0 universe, and Legion and I didn't think that was exactly nothing. It's a quantum state. It knows about the laws of quantum mechanics and so forth. You know, so we did not think that was exactly nothing. So the third one is what I would call really nothing. No quantum state, no nothing. You know, and I want to tell you what that looks like. Okay.
Wait, you just said no nothing.
Well. Okay, that's bad.
I'm just trying to, our vocabulary is going to start mattering really badly, as we go forward.
Grammarians will correct.
So don't tell me the nothing you're about to describe is not nothing.
That point, yeah.
Okay, go.
Okay, so what does really nothing look like? Well, what does it look like back here? Is there a big black thing back here? A big black cape over here on here? No. not Neo.
Okay, I'll stand over here. Now repeat that. Go.
It's not black back there. You don't have any retinal cells, looking in that direction. So that's really nothing. It's not anything. It's not there. And so Li-Jing Li and I thought that of Lincoln's model, which we thought was very interesting, what they're trying to do there is make quantum tunneling is weird. You can be in the room and then tunnel out without going through the wall, that kind of thing. It's weird, and so we are looking for something weird to start the universe.
Wait, just to get people on the same page of quantum tunneling. So quantum tunneling, if it happened in the real world, you'd be on one side of a mountain, and rather than having to climb up the mountain, come down the other side, you would instantaneously just appear on the other side. And quantum particles do this all the time. In fact, the sun cannot produce energy without a form of quantum tunneling, because there's a barrier in the way, and how do you get to the other side? And I think in the movie Buckaroo Banzai, in the 10th Dimension, he would go through mountains for just this way.
Oh, yeah.
Yeah, yeah. 3 of you saw that movie, apparently.
It's a great movie. It's about a rock star physicist. I like it.
He said, very wise, everywhere you go, there you are.
Exactly.
That's right. The quote of the movie, yes.
Great,
okay, so your nothing is not even anything, is what you're pointing
at. Yeah, and so we thought we'd try something different. We thought that it might be hard to make a universe out of nothing, particularly relying on something that by definition didn't exist. So we thought, well, maybe the universe isn't made out of nothing. It's made out of something. And that something could be itself. And so inflation allows you to do this. And
I knew there was something in there.
You knew there was something in there. Now this is the
Rich,
model.
do you have the universe in that Tupperware?
He never comes without a visual aid.
This is the model.
Universe in a Tupperware container, yes.
So here's a picture of our model. It looks like something Dr. Seuss invented. This glass represents space-time. We're showing one dimension of time going up this funnel here. This is an inflating universe here. The circumference is getting bigger as time goes up here. We're showing this is an inflating universe. And Linde, who's at Stanford, showed that quantum fluctuations that we've heard about can cause a universe to give birth to another universe here. And so this is a universe, baby universe, born. This is called chaotic inflation. This is a universe born by quantum fluctuations off of this one. It's a branch that grows up to be as big as this trunk, and then it can sprout branches of its own.
But so, Rich, you're holding in your hand 4 universes. Is that correct?
Just 4.
Yeah.
Fine, okay.
Yeah. It's not heavy. They're my universe. Okay. So these are 4 universes. Now, what intrigued Neil about this is that he say, well, what's outside here? What's this expanding into? Nothing. The only thing that's real here is the glass model itself. It's curved, it has a shape, but to visualize it, we put it in this background space, but the background space doesn't exist, just the glass itself. So here's a universe coming off here. So Li-Jing Li and I said, well, what about if one of the branches simply branched off here, circled back in time, and grew up to become the trunk? This is possible if you have a time travel solution in general relativity, of which they exist. It makes a little closed time loop here. And if you go, and the universe is inflating, so this branch gets bigger and bigger as it comes back here, and the trunk is bigger than the branch. And so if you're here, and you went around this, you would be able to come back in time and visit the event where you were. This is a time travel to the past in general relativity. This is what this looks like. Every event here has events that preceded and caused it in the usual way. So if you're here, there's an earlier event here. There's an earlier event here. There's an earlier event here. And so if you go back in time, you go back further and further, and then you start going around. It's like the Earth has no easternmost point, although it has, it's finite toward the east. And so we thought this might be useful for addressing the famous first cause problem. This universe is finite to the past, but it has no earliest event. And the interesting thing about this was that this geometry here explained the usual causal set of events we have where photons go only toward the future. If you shake a photon here, it goes out and intersects Alpha Centauri 4 years from now, because it's 4 light years away. Maxwell's equations allow what's called advanced waves that go to the past and would be shown intersecting Alpha Centauri 4 years ago. But we don't see them in nature. So it doesn't have anything to do with electrodynamics. It must have something to do with the beginning of the universe. So in this case, the only self-consistent solution for this is one where photons go toward the future. Because if you had one that came back here, it would come back here, go around an infinite amount of time, gaining energy all the time, and blow up and cause a singularity and not be the geometry you started with. That'd be like killing your grandmother. So you're not allowed to do that because you have to have a self-consistent solution. So it also explained the entropy area of time because this was cold.
Wait, so you're creating the universe out of itself rather than out of nothing?
Yes, we were asking the question, can the laws of physics allow the universe to create itself?
Are there laws of physics out here?
No.
There's nothing out there.
That's
so
real.
Okay, you happy with that?
No,
It's
I'm
not
not
even-
happy. What tells the abyss that it's pregnant with this thing?
That's,
It's finite in time. Every event has a cause. There's no first moment. Why does it exist? It
That's
exists
what
eternally.
Mr. Leibniz would say. And listen, Leibniz's answer was God. Leibniz, as they say, smart guy, invented calculus. Leibniz's question was, why is there something rather than nothing? We were just trying to answer the question, how did the universe get here? So if we say, given that the universe is here, how did it get here? This was a possible way to do it.
So, Rich, your universe always was. That's your answer.
Well, if I think four-dimensionally, like Einstein, I'd say I got this four-dimensional sculpture here that doesn't change. It's a four-dimensional thing. It exists. And so Mr. Leibniz would rightly ask, so why is it there? Instead of not there.
Or instead of something else.
Well,
Wait.
That evolved according to a completely different set
That's
of
what
laws.
he would
Yeah.
say
Charles,
if
Charles,
he were here.
we've
We
got-
didn't claim to answer that.
Charles, in your study of zero, you studied Eastern philosophy, right? And we have some people arguing over here about basically first causes, right? And I'm just curious, I don't study Eastern philosophy. Around the world, are people as disturbed at the need to have a first cause? Because that's what's driving all this. It's like, well, how did it get here? I have to know. It is a problem to be solved. Is there anyone in the world who's just cool with that?
I can't say I've studied philosophy as extensively as to answer that universally, but almost all mythologies.
University mean earthwide.
Earthwide.
In this house, universe means the universe, okay? So, like Miss Universe? No, she's Miss Earth, all right? Let's just establish that fact now.
Well,
Continue.
this Earth has the home planet advantage, so that's not fair.
That's right.
But basically, every mythology, more or less, needs a creation mythos of some sort. Basically, two functions of a mythology are explaining where we came from and where we're going. And
So the urge was there.
the urge was there. The urge was there.
Pre-scientific era.
but let me look. We don't need the point is science doesn't worry about a first cause. I mean, you're pretending it does, but it doesn't. Religion does. First of all, there are lots of good physical definitions of nothing, and I still think the best physical definition of nothing is the absence of something. So to understand nothing, you have
So
to
we're
understand.
done.
You have to understand what something is. That's why it's a physical question and not a philosophical one. First, you have to understand what something is, and you have to understand what the absence of that is. All those are physical questions, and physicists try to answer them. Now, there are a number of different answers which we can get to, and Rich has talked about some of them. There's still the simplest thing is not to take it to zero radius, which is, as Eva pointed out, is not physical. At least most of us think it's not physical. When you apply quantum mechanics to gravity, and we don't have a quantum gravity theory yet. Some people think we might be getting close, but we don't know if it is. But one of the things is quantum mechanics says things fluctuate. And if gravity is a theory of space and time, if you make space and time quantum mechanical variables, then it is perfectly possible for universes to pop into existence. Space and time
Larry?
to pop into existence where there was no space and time before.
Hold on.
Now,
Hold on.
hold on.
Hold
I
on.
haven't had
How
a
did-
chance to talk
hold
yet.
on.
so let me-
I must ask a question here.
What?
Space and time pop into existence. You make that sound like a temporal process, a process in time.
Well, because I
It's
said
not
so
a
you can
process in
understand
time.
it.
Huh?
No, I mean, I used words, and the problem with words
Right.
are, as T.S. Eliot says, they're sort of slippery.
Right.
Okay, how about this?
But becoming
Well, I know where he's
implies
coming-
time.
No, no.
You can't have time coming into existence
Yeah.
as itself a temporal process. That
Well-
makes no sense.
well,
That's
you
why
pop-
it's good to
you
have
create a
philosophers
closed-
around, which I'm
you
not one
create
to
a
help
closed-
you use language precisely.
And so let me just pretend there. Let me just say that there's a global time, and at some time a space pops into existence.
Okay,
Okay,
two
will that
times
make you happier?
Okay, there's
Okay,
a global
but-
time, and then
Just
there's
to
a...
clarify.
But the
Yeah, yeah,
point-
yeah.
Wait, I have to,
Okay.
just so I understand what's
We
going
have
on.
how many
So, wait,
nothings? We have global time. And
hold on,
okay,
just so I understand what's going on. Lawrence,
Mm-hmm.
you are saying that because we are illuminated by the actions of quantum physics mentally, we can think about whatever is our best understanding of nothing, and quantum physics then pops into existence in that nothing an entire universe. And if that's the case, I would then pick up Jim's point and ask
I was
you...
going to try and ask, where did the quantum physics come from?
No,
Is
no,
that
no,
what
no,
you're
no, no.
asking?
That's not what I'm going to ask you. I'm going to
Okay.
ask you, that had to happen at some point.
Why?
Why isn't it happening all the time,
It can
everywhere,
be.
at all times?
First of all, it can be, and it wouldn't be noticeable at all. Okay, it could be happening in our universe. You'd be popping off baby universes, but they would disappear from our universe.
Okay, why don't
wouldn't
you
see
like
them.
his nothing that he birthed his universe in?
But that's, okay.
Why don't you like his nothing? That sounded like a good
Well, first
nothing.
of all, as he himself admits, his nothing is a something. And
Well,
when you start with a
what is the
contradiction, you
something?
can derive anything.
Let me get to the point.
Go.
The key point is this question. First of all,
It's
the
a
question,
physical
why is there
object,
something...
it has structure, it obeys laws,
Hold-
complex
hold-
laws, there's a lot of
hold-
stuff going on.
hold-
I mean, my bank account, where there's no money in it, is still something. And,
Yeah,
and the
absolutely.
vacuum is a hell of a lot more of a something
okay,
than my
but-
bank account.
Okay, well, no, the point is that the key question is really, the why question is stupid. Okay, everyone who has kids knows that.
Wait,
I'm
which
not-
why
because
question are you talking about?
Eventually you keep saying, why, and the only answer is go to bed. Okay? and so the point is that what we really mean is how. That's what when we say why, what we really mean is how. We care how did it happen. Now the question isn't, was there something else that existed? The really amazing thing, the question that really matters, and it may not be the question that matters to some classical philosophers, but it's the question that really matters is, how did a universe of 400 billion galaxies containing 100 billion stars, how did that come into existence if there weren't galaxies, if there weren't stars, if there wasn't energy? And that is the question that physics is coming close to answering, and that may not be the ultimate question of whether there was nothing before that, but there was nothing, our universe didn't exist. And our universe coming into existence when it wasn't there in the beginning with zero energy, but still enough gravity to create everything we see is the amazing, remarkable miracle
It is
that
amazing.
science creates. And that's the important question.
Yeah, it's a great story. There's lots of empirical evidence for it. You've told a miraculous story about how a universe like ours was spawned by a piece of rubber. But where did the piece of rubber come from?
No, and the point is that even the laws don't have to exist. There could be in the multiverse.
Wait. You said a quantum fluctuation brings the universe into
That's
existence.
because I can talk in our universe about quantum mechanics, but it could be, although this is wild.
Nothing else we've been talking about until now is wild, but this is wild. Okay,
yeah,
go.
This is even wilder. Okay, so it's quite plausible. In fact, if there are many universes, as current theory
multiverse.
suggests, that in each of them, the laws of physics essentially come into existence when the universe comes into existence. There are different laws of physics
then
in
you
each
can't
universe.
invoke a quantum fluctuation
but
to give you the universe
but I
that has
don't know,
quantum fluctuations.
But what is interesting to me, and I have no mathematical underlying theory of this, but it's perfectly possible, it seems to me, that some of those universes don't have quantum mechanics. I don't know if quantum mechanics arose when our universe arose.
Ava, I keep calling you Ava.
I mean, I can only describe it mathematically by a theory right now, but I don't know. String theory is
Okay,
quantum
I-
field theory
okay.
applied.
I met
Okay.
Eva on the campus of Stanford a couple of months ago when I happened to be in town. And first time I met her, and she had already been invited to this, and we just chatted about nothing. And so she went on, and so it was something, but it was nothing, right? So we're chatting on, and then at one point, she described a nothing to me that just blew my mind. Okay, so Eva, could you give it, because the nothing you described to me just would send all of us home in 3 minutes, okay, because we're done after the nothing you described to me. I was like, I went out saying, damn, I can't even. So could you please just,
I'm not sure I could live down to that, but I'll try.
okay, just to give me that nothing, and you all just shut up and listen to this. Okay, go. Go.
Well, so I already said
I'll get a close listen on this. Okay, go.
All right. I already said my conservative view of nothing, which is inflationary density perturbations, but let me come to this more ambitious question that's being discussed. And there is a model, I think, for what you're referring to. It happens to be a model within string theory, but
Yeah.
maybe there would be more general approaches to that, which basically proceeds as follows. So space-time is an emergent thing. Large radius space-time is what we think is rather special. It's the exception rather than the rule. And it can evolve toward a singularity or evolve out of a singularity. But let's consider the case where it's evolving toward a singularity. And what can happen is time can keep going forever. But in effect, the masses of all the fields, including the graviton, exponentially grow. So there's a pretty controlled model of this in string theory. It's a classical version of what is called the Hartle-Hawking wave function. And so, we can make sense of that. We can do computations of, if we assume we're in the vacuum in this exponentially massive phase, we can ask, what does that state correspond to in the time periods when there is a large space-time? So we get an answer for that. It's a simple thermal distribution of particles. So, these are questions that we can begin to try and address using technical tools that we're developing. We're far from answering the ultimate questions. No one would ever say otherwise. But I don't
the
think,
fact that it's even plausible is what's
No,
really
you described something about dimensions and it went away?
Yes.
You're getting there. Okay.
Well, that's right. So as you, okay, so as you approach this phase, you can make this count of the density of states that I alluded to earlier. So you can ask within string theory, what is dimensionality anyway? Since large space is the exception, there we can just count dimensions by asking how many directions we can move in. More generally, we can't do that. So one thing you can do that's a little more general is to ask, how many dimensions in effect can a string oscillate into? And that affects the density of states that the string carries. So how many different states of the system you can have. So if you have a string, it oscillates, and it has more states if it can oscillate in more dimensions, but you don't have to have a large space-time in order to ask the question of what is the density of states of a string.
But just to clarify, if you have a string that's just sort of in 2 dimensions, you can jiggle it and it'll wiggle that way. If you have 3 dimensions, it can wiggle in more ways.
In more ways.
4 dimensions, it goes out of what your awareness is. And so
the number of states actually grows like the exponential of the square root of the number of dimensions when there's a normal notion of dimensions.
I was going to tell you that,
Yeah. So what you do is you define an effective dimension where you just ask, this is growing like e to the something, like exponential of something, and you define that something as the square root of the effective number of dimensions. And now that quantity can change, and as you go toward a singularity like what we're talking about, it can decrease, and I think that's what we were talking about.
And it decreases until what happens?
Well, the best way of describing it in words is that the masses of everything grow exponentially as you approach this point.
But that's not what you told me in your office. No, you told me that there's some state where all the dimensions go away themselves.
Well, that's what I'm saying. So as you go.
Oh, that was what you were saying. I'm sorry, I missed that.
No. Okay, let me try and close the gap. So I've said 2 things, I guess. One is that, in effect, the masses are growing exponentially, and then I've also said you can measure the effective dimension by asking about the density of states. So let me just say, as you go toward this phase where the masses are growing exponentially, that number, the effects of dimensionality, is decreasing.
Until
0.
Until you don't even have dimensions.
Right.
Okay, so your flugelhorn theory here, that's in some dimensionality, isn't it?
Well,
It's embedded in something that presumably has a larger dimension than what it's embedded in.
It just has the number of dimensions it has, which I'm saying is 4, you know.
Yeah, but it exists in a...
No, that's just to help you visualize it. Out there is nothing.
In string theory, you can. I mean, the string theory can predict many universes with all sorts of dimensions, and four-dimensional universes might pop into existence, and six-dimensional universes and two-dimensional universes. We don't happen to live in those.
Okay, is there a highest number of dimensions that could possibly represent reality?
Well, it depends on the theory, I suppose. One might say 10.
That's a
10
cop-out answer. I just want you to know.
No, let me very quickly address that. You're about to say 10. 10 is a special dimension in string theory because it is the dimension in which you have what is called supersymmetry, extra symmetry. But it's in no way predicted by the theory. In fact, you can start, as you were just saying, in any number of dimensions. The difference between any other dimension than 10 and dimension 10 is that in any other dimension, there's potential energy from the start in your analysis. That's the only difference.
But the point about this is that the answer to the question is really, it has to be, it's not, the interesting question is not why is there something rather than nothing. The amazing question would be why is there nothing rather than something, but we wouldn't be here to ask the question. If
It's not.
But I mean, the point is it would be amazing to have nothing. There's always going to be something. It's going to rise sometime, somewhere, and you happen to live where it is.
Charles, did people debate zero when it was first introduced?
Yeah, it was a...
Who didn't like it?
Well, zero was hated by the Greeks in particular because
So they didn't have bank accounts that went to zero, like like Jim's bank account.
they only had zero for Jim's bank account when they borrowed from the Babylonians. They actually did. They did astronomical calculations in Greek numbers, and then when they realized they needed a zero to make the calculations easier, they would swap into base 60 and use Babylonian zero and the symbol for
They
zero.
did take from the Babylonians.
They took it from the Babylonians, but they
Base
didn't...
60, so we owe our measurement of the clock time to them, which is
That's
essentially base 60.
That's
60
correct.
seconds in a minute, 60 minutes in an hour.
That's correct. And,
Okay.
and it was so repulsive to the Greeks that they refused to incorporate it into their own system. That it was basically a calculational tool that was used by the geeky astronomers, and we forget about it the rest of the time.
So is there some modern counterpart? Because we're still human, just as they were, and we have a philosophically informed gentleman here who just can't stand what's going on to his right. And they're grappling over some physical representation of nothing, and he's saying, whatever you've done, you still haven't given us nothing. So is this just the same argument moving forward?
I think in terms of, there's an aesthetic underlying fight here.
Because Lawrence loves his zero, his universe from nothing. He's aesthetically turned on by that. I can feel it when I walk near him. Okay?
That's just personal attraction.
Yeah, I mean, there's all sorts of things that some of us, it takes time to change your aesthetics to accept. I mean, if you look
What
at
you're saying is some of the resistance was philosophically driven rather than practically driven.
Absolutely.
Okay.
Absolutely. If you look at the turn of the century, I mean...
No, we got to really specify which century you're talking about now.
the turn of the 1900.
Okay, thank you.
If you look at that time, that the atomic theory was relatively new, and modern atomic theory was relatively new, and there were physicists
Just to
who were out
clarify,
there...
the atom was still a controversial topic even in 1900, if I remember
Oh
correctly.
yeah, it wasn't accepted till after 1905.
Yeah.
There were big conferences on no
So
atoms.
Brownian motion, I guess.
Yeah, really, Einstein.
Einstein.
And-
Okay.
I think it was
and
Ernst Mach who said, if atoms are true, I'm resigning. I'm giving up my position. Similarly,
And he was begging in the street, a few weeks later.
Exactly.
Okay.
He didn't believe in quantum mechanics either. Planck, essentially, even though he invented it.
and Einstein, even though he was one
Yeah,
of the founders
even though
of
he
quantum
invented it as
mechanics,
well. Yeah.
found it aesthetically repulsive. And some of his best contributions, were trying to show that it was garbage.
But that's what's great about science. It takes what's aesthetically repulsive. It says the universe doesn't exist to please you. You may like it, but it doesn't matter. It may not be true.
Yeah, but
and if
Jim
it's true,
Holt
you got to
wants-
learn to like it.
Jim Holt wants the universe to please him.
No,
Yeah.
it's a crappy, mediocre universe. It's badly designed. No, I mean, the most interesting, the father of chaotic inflation, Andre Linde, told me that it would not be hard for a
Just a
slightly more
departmental colleague of
Yes,
of
that's
Eva
right. To
in
make a
Stanford.
universe in a lab, a hacker physicist in another universe could make a universe like ours in a lab with just 10 to the minus ninth grams of matter. And in fact, when you look at how imperfect and weird our universe is, it probably was made by a hacker. I mean, maybe there was a creator, but certainly not an omniscient.
Wait. You're saying
No, why are there 60 plus elementary particles? That is so inelegant. If I were designing a universe, it would be far more elegant than that.
It would have, it actually would
And
have
why
nothing
is
in
that-
it, probably.
So
No, I mean,
why
a
four
universe that's empty
forces?
is
Why all
beautiful.
these? Why all this symmetry breaking?
No. In
why
fact,
all these-
people say one of the things that I really hate, and I've debated recently in Sweden with theologians, is they say, well, they get this stuff that physicists talk about fine-tuning. They make it sound as if our universe is beautifully fine-tuned for life. It's actually could be much more beautiful and have life in it. And it turns out that there are lots of constants we don't understand, and they look unnatural. And maybe they are, and maybe it's fine-tuned, but it doesn't mean it's the best universe. But again, what's surprising about that? Bees can see the colors. It's cosmic natural selection. Bees can see the colors of flowers because they couldn't reproduce. If the constants in nature happen to allow us to exist, but that's not so surprising. What would be more surprising is they didn't, and we still did.
Rich, what's the famous quote from Alphonse X? Oh,
There you go. That's
I thought
question.
you were going to say, is this the best of all possible worlds?
no, Alphonse. Nobody remembers
have-
this quote.
Is that it?
Alphonse X? No.
Why don't you tell
No,
us?
that's Leibniz. Leibniz again.
Leibniz.
Is this the
Okay.
best of all possible
Alphonse
worlds?
X was it the 1300s, something around there. He said, "Had I been around at the time of creation, I could have given some suggestions for God to have improved
Okay.
His work."
Okay.
Right. Upon looking at the actual vagaries of nature.
There's a lot of folks like that. Anyway,
Well, so Rich, I remember.
here's something nice. Here's something nice about the multiverse. I mean, what we know about the Big Bang is the Big Bang seems to be started by inflation. This is gravitational repulsion from the negative pressure that started the Big Bang explosion. And it seems to make multiple universes. Well, you saw 4 of them here. And there's no stopping it. And so it just keeps on making more and more universes. So, and I proposed the early model of this in 1982, a multiverse with all these different universes. And Linde has quite said that, the laws of physics in these different bubble universes or these different branch universes can be quite different. So now here's the
different
nice...
in laws of physics.
Yeah.
Different
Well,
laws of
but
physics.
not that
Martin
different.
Rees would say they're different. There's one
they're all low
laws
energy.
of physics, which is sort of string theory, let's say, and there's different bylaws here, and there's bylaws here, because the different vacuum states and the different multi-universes evoke different laws of physics. And so here's the nice thing. If you have a multiverse with an infinite number of universes here, some of them are nicer than others. Some of them are completely hostile and, they're really hot and no intelligent life can live over there. And so, luckily, you don't live over there. and the universes that are more habitable, more people will live in. This is the anthropic principle. So some universes are populated by more intelligent beings. Some universes are populated by less intelligent beings. And so you're likely to live in one of the nice universes.
But,
Thank you.
Exactly. But, our universe is actually pretty hostile. I always get amazed when people say
Yes,
our
completely
universe is
hostile.
friendly to life. Most of our universe is damn hostile.
Yeah, the universe wants to kill us at every opportunity
It's
it has.
amazing we've been here this long.
Remember that asteroid that just came?
I mean,
that's
it's amazing.
example.
There will be another one coming in the future. The universe is out to kill us and has been since we've been evolved. And
Jim.
And in
But
fact,
still.
it's not so clear that. In fact, there are dangers of using the anthropic argument too, because it assumes typicality. I often say, if you use the anthropic argument for intelligent life, we should be having this discussion underwater.
Just to clarify, the
Three-quarters of the Earth is underwater.
of
No,
the surface of the
I
Earth.
would say-
Right. So wait. So the anthropic principle, just to put everyone on the same page, is the premise that you can marvel at whatever universe we're in for whatever regions, Most of those occasions are theological, yet, but the anthropic argument would say, correct me if I mess this up, I think I have it right. So the universe that allows you to make that argument is the universe that allows you to exist to make that argument. And so there are people who want to then say the universe was made for us.
Well, the point is there are people who say, and we said it, physicists have said it for many different times over the last century, it's always been wrong, but maybe it's right this time. There's some quantities, like the energy of empty space, that seem so inexplicable from a fundamental physics perspective that people are saying, well, it is true that if it was much bigger than what it is, there'd be no galaxies. If there are galaxies, there'd be stars, no planets, no astronomers. So the universe is the way it is, so there are astronomers to measure it. And it sounds religious, but it's really, or tautological, but it's not. It could be true that it's kind of a cosmic natural selection. As I say, you just find yourself living in universes in which you can live. It's perfectly plausible. Where I take umbrage at it is some people who then make the claim that they can argue, they can understand why the fundamental constants are what they are, but that makes some presumptions about typicality, about us being typical life forms. And I don't happen to think we're typical life forms. We happen to exist pretty early on in the history of a universe that looks like it's going to exist a lot longer. And I suspect
trillions of years.
I suspect there'll be lots of life forms that are quite different from us in the future. So I don't think we're necessarily typical. We just happen to be here.
Jim, every time you've opened your mouth, it has been in part to pass judgment on other people's offerings of a nothing. Do you actually have a nothing to put on the table other than arguments against other nothings that come before you?
No, I mean, first of all,
Okay.
I would say philosophers have talked a great deal of nonsense about nothing. And if you look at the philosophers who've addressed nothing in the history of philosophy, the earliest one was Parmenides, the Eleatic sage, and he said that we cannot speak of what is not. And in saying that, he violated his own precepts. So he got off to a very shaky start. Then we have Hegel saying
Wait,
that
the act of saying
pure
you
being,
can't speak of what is not meant he was speaking of what is not.
Exactly.
Okay.
Yes, exactly. Yeah.
Okay.
We can speak of what is not. I can speak, for example, I was going to make a very bad joke. So moving on to Hegel. Hegel said, what is pure being? Pure, indeterminate being. It has no qualities. It's the same thing as nothing. So Hegel said being equals nothingness, which is a great deal, very close to what you say. Also nonsense, but harmless nonsense.
Thank you.
Heidegger thought of nothing as an annihilating force that sucks things into existence and keeps them there, kind of like the vacuum cleaner in Yellow Submarine that sort of sucks up all the scenery and sucks up the beetles, and it sucks up itself, and it nothings himself, and then the world pops back into existence.
The 60s was good to him. Yeah, okay.
And so, but analytic philosophers, serious philosophers in the tradition that I think is the greatest today, say, that nothing is, it's a noun, so it seems like a name for an entity, but it's not. It just means not anything. There's nothing particularly mysterious about it. And so nothingness is a state in which there's not anything, period, including fields in vacuum and so forth.
But there's no vacuum.
But then we should ask, why do we assume that the fact that there's a world rather than nothing requires an explanation? What's so special about nothing? And people say, well, nothing is the simplest. Does
everybody require that explanation that you've seen around the world? Because you said it requires it, but that could be a Western mandate that we've put upon ourselves.
The creation myth is always about how the world we live in came into existence. It may have evolved from an earlier chaotic state, or it may have been created out of nothingness by a god or something like that. There's only one, by the way, there's an Amazon tribe called the Pitaha, who I think is the only civilization known that doesn't have any creation myth at all. When they ask about the world, they say, it's always been like this.
Like Rich's thing. So Rich came from that tribe.
Physics would also always say, I mean, we're used to in quantum mechanics realizing that any possibility, anything that's possible, can exist.
Yeah.
And so the simplest answer is if a universe is possible, it has to exist. And it's not too surprising to find ourselves in it.
We're running low on time.
But there are lots of other possible universes that don't exist. So yes.
How do you know they don't exist? You sound like you've been there and looked for them and couldn't find them.
So that's interesting. You're positing a sort of a principle. It's traditionally called the principle of plenitude or fecundity. that every possibility is actual.
No, I'm
that
just-
there are universes
no, I'm not
that,
saying
are,
that.
that are
I'm
ruled
saying you're
over
saying-
by Greek gods and so forth. That's an interesting
That's not what I
metaphysical
said.
idea.
You said
Yeah.
that other kinds of universes don't exist. I just don't know how you have access to that information.
No, I don't. It's possible that every possible universe governed by every imaginable combination of laws, and even completely lawless universes, it may all exist out there. So it's conceivable that every possibility is realized. I mean, this is an idea that goes back to Plato, and actually Steven Weinberg, who's the father of the standard model of particle physics, entertains this notion in his book, Dreams of a Final Theory, The Principle of Plenitude. It would explain why this world exists. This world is just one world in an ensemble of all possible worlds. And one of these possible worlds is the null world. It's nothingness. So in answer to the question, why is there something rather than nothing, you answer, well, there's not. There's both. So that, that's one way. I think that's a very extravagant metaphysical.
Very rare. I mean, the point is most of the worlds are not null. And that's why it's not too surprising to find yourself in not a null universe.
But why do we think that the null universe is the ontological default option? That's what's it is the simplest. It's it seems to be the least arbitrary. It's the cheapest. It doesn't cost anything. But actually, our universe is pretty cheap too. It has zero net energy. It's like Donald Trump, lots of assets and lots of.
But we have zero energy.
debts,
Our universe. My point is, our
working.
universe has zero energy. It's no different than our universe. Our total energy of our universe is probably zero.
Yeah. So our universe
That's
is
what
a
makes
cheap
it so
energy. Yeah,
special.
it's sort
That's
of a
what makes
free
it
lunch. in
likely
that
to come
sense.
from.
Yeah.
I want to go along the line here. We're running low on time. Plus, I want to make sure we have time for questions from the audience, from our Twitter stream, and from our overflow rooms. What's the best, cleanest expression of zero you know?
I think the mathematical expression where you start with zero and you remove it and you get the null set. That's my favorite. Nothing. Maybe that's the
But you start with zero and...
You remove it and you get the null set. It's almost a platonic nothing, which is...
Wait, so there's a zero, which is nothing, but then you remove the zero and you have a set of things that doesn't even include nothing.
That's correct.
That's an awesome nothing.
It is the emptiness of all. There's nothing.
It's so
at all.
empty it doesn't even have zero.
That's right.
Oh, that's
you can actually create zero out of the null set if you try.
You can create zero out of the null set.
There's a mathematical formalism that allows you to take the set of the null set and put it in a set, and that becomes zero.
Okay, I'm moving on right now. Okay. So Jim, your best nothing is what?
Not anything. That's the theory of nothingness. I'm sorry. It's no more interesting than that. And that's why, by the way, philosophers spend very little time vexing over the concept of nothingness. It's not that complicated.
So
Yeah,
all the
although
philosophers...
hard to imagine. Once again, professional bullying on television.
Wait. So Jim, so you're saying all the philosophers who are still arguing nothing should just listen to you?
No, they don't spend. It's not a fruitful philosophical notion unless you make heavy weather of it the way Heidegger did and say it's this annihilating force that should inspire angst within our breast. I mean, that's kind of fun. Or to imagine, the world is a little sealed container of being surrounded, floating in a sea of nothingness, and a little bit of nothingness leaks in when we go into the cafe and we expect to see
Did you
Pierre
use the word
there,
angst?
and Pierre. Yeah,
okay. I just
it's the
thought
Upper
it
West
just caught up
Side.
with that
It's
sentence.
It's a philosophical term.
So nothingness induces angst in us.
Yes, in me it induces jollity. We all have different temperamental reactions to it.
Rich, you seem to be pretty cool with nothing.
Well, I'd say not there. What does it look like? What color is that? I mean,
Okay. So that's not even
there.
black. It's not even a...
black. No, it's just not there.
So Rich, is it fair for me, I don't want to stretch your analogy here, because that was a good one. So people ask, what happens to you when you die? You go to heaven or hell or wherever. And for me, the simplest explanation is your awareness is such as what you knew of the world before you were born.
Exactly.
Right? And so that's as nothing as you can possibly come up, other than Shirley MacLaine, who's been reborn many times. For the rest of us, that's like what's behind your head, right? Because you don't even see it. You don't even know to think it's there. So your consciousness before you were born, that's a pretty good nothing, isn't it?
Who knows?
Listen, we're all going to enter that state tonight, by the way,
I
when we
use
go to
this
sleep.
example because it's like right here.
Okay. What are you saying, Jim?
Dreamless sleep. We'll all enter that state tonight for a little while. We'll have a little period of nothingness tonight during our dreamless sleep. And,
So there's no, yeah. That's
we
like-
don't have to think, what was going on before we were born. We dip into nothingness every night if we're lucky.
The absence of consciousness is probably the least satisfying.
Lawrence,
nothing.
what's your best nothing? You have a whole book on this.
Yeah.
By the way, all four of these gentlemen have books this evening offered for sale outside. We'll be at a table for signing. Eva has to actually leave for Europe tonight, so she won't be able to join us at the table. So, Lawrence, what is your best nothing?
Well,
Is it the whole universe itself? Because I wore a vest for you tonight.
Yeah.
Okay?
Yeah.
I just want to say, I've got the entire universe on my vest. And
I knew it would come out sometime. I knew it.
you tell me all these stars, moons, planets, came from nothing.
Yep. Look, there are a variety of forms of nothing, and different one, and they all have physical definitions, and you might not like any of them, but one is empty space, the other is no space, and the other's no space, no time, no particles, no laws, and that to me is as close to nothing as you can get. And in fact, as I see, I don't see why people have any problems with it. Each of these lights in this room emits a photon. The photon wasn't there before it was emitted. It wasn't in the electron. It wasn't in the atom. It was created from nothing. And some people don't have a problem with that.
No, it's created
The
from
same
energy.
thing-
Created
same
from
thing that
energy.
happened-
Lawrence, it was created from energy. And energy is not nothing. So I won't accept your photon.
Well,
analog.
it could. A zero
Back up
energy,
and say something
sorry,
else.
a zero energy photon. A zero energy photon. Our universe could be like a zero energy photon, a zero energy total universe. And again, as I say, if you imagine that process and ask what the properties of such a universe would be, it would look like ours. But I will accede, as I've always said, and I say at the beginning of my book, that I will accede that the philosophers and theologians are, know much more because they are experts at nothing.
Not even humorous.
So just Lawrence, just to close this out. So your universe that's created out of nothing, where there are no laws, no space, no time, no anything, that nothing had to know to create the universe.
Well, there may have been something else there, but our universe
Oh,
was
now
there.
you confess. I'm just trying to
Yeah, there
understand,
was
because
nothing.
if there's no laws, then there's nothing to know to create a universe.
What if there's every law? Is that the same as no laws? That's the
I
point.
bet.
Well, I think Jim was sort of saying.
I wasn't
Jim was
listening. What was
alluding
it?
that to every possible law, every possible universe. There may be universes with no laws, or maybe universes with laws. That's certainly a possibility.
All I'm saying is, if you have a place, whatever that is,
There was
where
no
there's-
place.
If you
You're
have a
thinking
no
wrong.
place with no laws, and then you birth a universe, something in that place had to know to birth that universe.
Why?
Okay.
Why, if it's
maybe not.
possible? Why do you have to? You're assuming intentionality. You're making this.
Eva.
something you
There,
don't
you're,
even
you're
agree
purporting
with
to
in-
offer
in
us an
theology.
explanation, and
What?
you're offering us no explanation. All you're saying, it just is.
Yeah, he's kind of doing
Yeah,
that.
you're
Eva,
not talking about a process that's governed by
it's-
laws,
we
by
say,
rules,
but
in which
we say
initial
what the
conditions
rules
you're
are
just
that
saying.
caused our universe, but we don't ask, what happened before. Because
do we have control over their microphones? Eva,
I would
give me your
just-
best argument for nothing.
I would just describe it as the absence of degrees of freedom. If you think about quantum field theory, again, just
We
as-
do that all the time. Think about quantum field theory.
Yes. What you do with it is you think about it on longer and longer distance scales, and there's a precise sense in which, as you do that, you lose degrees of freedom. And in a case of quantum field theories which have a gap between the ground state and the first excited energy level, as you course grain over longer and longer scales, eventually you come to a place where you've lost all the degrees of freedom. So the ground state of a gapped quantum system would be my answer.
The ground state of a gapped quantum system is your best nothing.
Yeah, I like that.
Okay. I kind of, my favorite nothing, not that anyone asked, but I will offer it because I'm host of the evening. My favorite nothing, I think, is what's outside of Rich's 4 universes. I kind of liked that because you have no access to it. It's not even anything, and it's behind the head of each of those universes. And I'm kind of leaning towards that.
It doesn't even exist, which you may also like.
So let me offer just a final reflection on this. It seems to me that there was surely a time when nothing was just I would say there's nothing between me and you. Then we learn that there's air, there's actual substance there's mass, there's energy, and so you couldn't call that nothing anymore. And then we learned that space has no air, and that's a relatively recent understanding. As late as the early 1600s, there were arguments that maybe you could fly to the moon, and by learned scientists. And the only way you could do that is if this air substance permeated the space between us and the moon. So now that when there's no air, so then space is the nothing, but then quantum physics, relativity tells us there's stuff going on even in empty space. So that removes that from our nothingness. And now we have to actually exit the universe, either sort of theoretically in the sense that Eva is suggesting, or outside because you created a model that we can look outside the universe. Now that's a nothing. And I just wonder whether this nothing is an all-elusive moving target, that one day we will learn that you do create those universes out of a law of physics. It's the universe birthing law. And then there's a law in the place where we previously thought there was nothing. And then that just simply pushes the definition of nothing that much farther away that you have to chase it down, because then the space that has the law that we previously thought was nothing that birthed the universe, you can then ask, what birthed that? So maybe nothing will never be resolved, and the only person who's content in his definition of nothing and it'll be permanent forever is Charles right here with his null set. Join me in thanking the panel for this. So we have two microphones up front. Feel free to line up. We'll spend 10 minutes, 15 minutes answering questions, then we call it a night. Okay, so we actually have questions in from Twitter. If you don't know what Twitter is, it's an extraordinary way to waste your time. Not quite as bad as Facebook, but it's up there. Okay, what are some of the practical, I'm going to take this to Lawrence. What are some of the this is from PsychMez1 on Twitter. What are some of the practical applications that can come from the discovery that nothing is unstable and creates particles? Is there any practical application for that?
Well, in quantum mechanics, there is. When one's talking about a universe, I should say proudly, there's no practical application I can think of to any of the work I do. And that's fine with me. In fact, it always amazes me.
Well, who pays your salary?
Well,
is it fine with them?
No, but look,
I think that's the question.
Neil, but the point is, people never ask what's the practical significance of a Mozart symphony or a Picasso painting. It's part of what makes being human worth being human, and the ideas of science are among the most beautiful intellectual discoveries that humanity's ever come up with. It doesn't need anything practical. But the idea that particles can spontaneously pop into existence is a very important practical aspect of all quantum mechanics. And in fact, in certain high fields and even in certain transistors and semiconductors, it's an integral part of modern technology.
So it does have practical application?
Yeah, of course, absolutely.
Okay.
But it doesn't need to be interesting.
Excellent. Next question, Capital Gambit, and this is from Twitter. What is more conceptually problematic? I'll take this to you, Charles. Nothing or infinity?
They're actually quite related. That infinity and nothing are almost two sides of the same coin.
So they have equal challenges to grasp.
That's right. That's right. If you think about,
except he has nothing in his bank account, and if he had an infinite amount of money, he wouldn't be complaining.
But the money would be worthless. So but a mathematical definition of the infinite is a set of stuff which you can take away from, and it's still the same size. And if you think about nothingness, you take away from it, it's still the same. So there's a lot of properties in common with nothing and infinity. In fact, part of the reason that nothing is so problematic is because when you're staring at nothing, you're looking down the face of infinity.
Wait, I thought if you take away from zero, you get negative numbers.
That's true.
But you just said you take away from zero, you still get zero.
Well, if you remove 0 from the set, you get the null set. But if you take away from 0, you get negative numbers unless you're going in the opposite direction.
Right, but you didn't say that a moment ago. I'm just calling you out on that.
Yeah, you're right.
Okay, good. Okay, thank you. Right here, first question up.
I have to ask this because I'm a biologist, which means essentially an experimentalist. Is there any evidence of nothing?
There's evidence.
Wait, Eva, go.
Okay.
So there's evidence of this inflationary theory that we keep talking about. The cosmic microwave background has a certain structure in it, in its fluctuations. So the so-called acoustic peaks in the power spectrum come about because of the initial conditions that inflation gives us.
But there's much. But as a biologist, you wouldn't be here. It turns out that the empty space that you may have learned in high school that protons are, if you're a good high school, protons are made of 3 quarks. We lied. They are made of 3 quarks, but in fact the quarks account for very little mass of the proton. Most of the mass of the proton comes from the fluctuations in empty space, in the nothingness of the proton. We can actually calculate it. And we get, in fact, a Nobel Prize was given recently for the theory that allows us to calculate that. So we know that these weird things are happening in empty space. And
This third nothing that isn't vacuum, isn't empty space. Is there any evidence of that? Of course there's vacuum, but is there nothing?
You mean no space?
Yeah. There's no experimental evidence of that.
No, absolutely, because we happen to live in space.
So if you put the experiment in the place where there's nothing, then the nothing is no longer nothing. It's got your experiment in it.
Yeah.
To measure the nothing. So then you can't ever measure nothing.
Well, that's there.
But that's the point. That's why it's not so surprising that there's something, because we couldn't ask the question if there was nothing.
All right. We'll get to this in a minute. Here, next one over here.
Oh, I'm a physicist and not a theologian, but since you guys and the lady began with a philosophical and theological, would anyone care to comment on at least my understanding of the Hebrew Bible, which begins Bereshit, which is the indefinite article in a beginning, not the beginning as it's translated into English. Anybody have any comments on that philosophy?
You started this, so let's go back over to you. So the question is, I don't read Hebrew, so I just trust what he says, that in the Hebrew Bible, it doesn't says, apparently it says in a beginning rather than the beginning.
Bereshit, not Bereshit.
Well, I don't speak Hebrew myself, but in my studies, I've looked at commentary, and again, you're absolutely correct that some versions, and I didn't know that the Hebrew version said this as well, but it is indefinite as to whether there was a prior beginning. That in fact, it's much more explicit in the Greek version that in fact, there might have been a prior existence and it had collapsed and there was a void. So, I mean, that's consistent.
But that's one of the reasons why it's so ridiculous to talk about theology when you're trying to explain the universe, because, you know, God speak Hebrew or Greek or Aramaic or Arabic. I mean, it's ridiculous.
Spoke English.
Doesn't explain
We know
anything.
Right.
I mean, they didn't even know the Earth orbited the sun, so why are we listening to them?
Next, right here.
My definition, my very basic definition of the universe is always everything. So the idea of a multiverse, and you're saying during a quantum fluctuation, a new universe is born. Why is that a new universe and not something that's part of the pre-existing universe? And
That's
what
Rich,
is a
why don't you take
universe
that,
if
Rich?
The multiverse is everything.
Well, the reason we use the
Just
word...
to clarify the question, he's saying if the universe is everything, why distinguish our universe from others that pop up in such a thing as the multiverse? Why even make that distinction? It's all the universe. Go.
Well, we use the word multiverse because these are expanding so fast that, as I said, event horizons arise between them. If you're in one of these funnels, light from the other funnel can never get to you. So we can never observe those other universes. So that's why we use that. That's why we use that word.
So universe is not everything; it's everything that you can interact with.
Or could have ever. The new definition of the universe is everything you could have once interacted with or you can ever interact with. So everything you can have physical contact with, either in the past or the future, is a universe. And everything that you can't have is not part of our universe. That's our modern definition.
Modern? How modern is that?
It's a good question.
But they
I don't know
all,
probably since we just thought of multiverse.
but these other universes are connected to us through the trunk of the tree. If you imagine it's a tree with many, many branches, we're on this branch over here. We can't see what happened on these other branches, but all of us have come from one trunk, which is the original inflating state.
But that's in that version. There could be other versions like string theory where there are literally universes that were never in causal contact.
Sure.
Okay.
If that can happen one place, it could happen another.
Next, right
It could
here,
happen
sir.
More than once.
Number one, thank you all for really making it our minds expand with these things. But
Or implode.
Or implode. Either way, it's action of the brain, which is good. Do you ever feel that as long as we're locked within the confines of our human consciousness, that we're just fish trying to understand the land? And you up there remind me of flying fish that get a better view for a little longer than most. But are we really futilely listening to something about the Big Bang and the universe that may never really get there at all?
What he's saying is, how stupid do we think we are?
Well, look.
That's the question.
No, but
Jim,
it's
Jim.
a really profound.
No, I got Jim.
Okay.
Pick that up.
Okay.
Did I characterize your question accurately?
You did. I
Okay.
mean, the thing is, it reminds me of a car without positive traction, with only one wheel spinning in the snow. Are we ever going
We all
to get
saw
all
that
four
movie. It
wheels
was a
and
good movie.
drive?
Yes. Okay, go.
State-of-the-art physics does not give us any satisfying picture of how the world is. According to state-of-the-art physics, there's this one thing called, a system, call it U for the universe, and it has a very complicated state, which is a point in an infinite dimensional Hilbert space, and the state that it's in is determined by Hamiltonian, and this is what reality is. It's not tables and chairs and rocks. And so when I see a bowl of cherries on the table, all I see is that the system U is in a certain region of the Hilbert space. That is the picture that physics gives us of reality. It's a terrible picture. I mean, quantum mechanics makes no sense.
You're agreeing that we're all too stupid.
And people say, just shut up and calculate. It works beautifully. So it's empirically adequate. It explains all the observational evidence, but it doesn't give us a satisfying picture of reality. So I think we talk very cavalierly about why there's something rather than nothing. We have the feeblest grasp of what something is and what existence is.
But it's worse than that. It's empirically.
Wait,
No.
If it's worse than that, I don't need to know about it. Okay.
No, empirically, we're limited by the fact that we happen to have evolved at 14 billion years, or roughly, into the history of the universe. There are questions we will never be able to answer because of the accident of our birth. And what's amazing is we're coming pretty close to some of them, and that's amazing. But we didn't have to. 20 years ago, 30 years ago, we weren't thinking some of these questions.
Wait.
We're forever limited in our knowledge, and that's just life.
Lawrence, you're suggesting we're limited in knowledge because we're born at one time and not another time, rather than just that we're too stupid.
Well, it's a combination. We also may have limits in our brains.
I want you to admit that. Okay.
Yeah.
Sir, yes.
I was going to admit it for you, but I'm sorry.
Sir.
I simply want to follow up on the question that asked earlier. Multi-universes, you're simply kicking the can down the road. Because at the end of that, you're going to ask it, nothing, and then there is another aspect of it because theological. Do you follow me?
No, I didn't follow it. Did you?
Let me reflect on it for a moment, okay? I've thought about this recently. The universe, we have come to learn with hard-earned science research, the universe doesn't make anything in ones, okay? We imagined that Earth was sort of unique among objects, and we found it was just one of a bunch of planets in orbit around a star that was pretty special to us. And then we learned it's just one of 100 billion stars in our galaxy. Well, the galaxy was special up until 1920. Then we had this debate about whether the galaxy is all there is or there's something else outside of it. We learned there are island galaxies out there, billions of them. And so then we have this universe. That's the one universe in which we're all contained. So maybe the universe doesn't even come in ones. And if that's the case, the multiverse picks this up, and then you have multiple universes. But that leaves me to ask the question, which we will not answer today, if nothing ever comes in ones, not even a universe, then would that possibly mean that the multiverse doesn't even come in ones?
Sure.
It's just, He said we're still kicking the can down the road, and I bet you Jim Holt would agree.
Whether there is nothing, or the other alternative is theological. It's God.
Well, there can be alternatives that are not always religious. That's an interesting false dichotomy that's often set up. If it's not this, it must be religious. No, if it's not this, it could be other stuff you haven't thought of yet. You can't assert an answer just because it's not something else. And it's a false argument that's been made throughout time. And the better scientists, as they move forward, never assume anything just because one thing is wrong. Yeah. Okay, right here, sir. We'll go another 5 minutes and we'll call it a night. Thank you. Yes.
Hi there. Good evening.
Good evening.
You guys mentioned quantum tunneling earlier, right? Which is
Isn't that cool, quantum tunneling?
Oh my God!
I would so want a quantum tunnel.
So I'm really glad that you're excited to talk about this. So you mentioned you can pretty much like go through a mountain without going up or around it, and a mountain being something. I read a couple of years ago that scientists were able to teleport electrons through a vacuum, like a distance of like nominal distance, like 9 meters or something like that, through a vacuum, which is pretty much nothing. It's the same thing that space is made out of. So is there really anything that's holding us back from with quantum tunneling and teleportation through vacuums, stopping us from taking things that are actual tangible objects and being able to teleport them? Is that something?
Okay,
something that's achievable?
Okay, I think we got to go to Lawrence on this because he wrote a book called The Physics of Star Trek.
Yeah, true.
Okay, all of
Yeah, no, I was going to say yes. So the answer, the answer is that it was really good public relations for people to call it quantum teleportation, and the answer is we can do strange things with electrons and photons, specifically because we can prepare them in very special quantum mechanical states. So we can do remarkable things with photons and electrons because we can prepare them in a very special quantum mechanical state and create these things called quantum correlations, which you don't need to go into, that allow you to do strange, miraculous, and crazy things.
At a distance.
Yes,
simultaneously.
But we are not specially prepared quantum mechanical states. And therefore, we can teleport quantum mechanical states, but you and I have to take airplanes. Okay.
Okay.
I wish it wasn't the case.
Sir, right here, go.
I noticed throughout the talk that nobody seemed to strongly object to the idea of the degenerate state. Some people thought it might be a futile abstraction, and some thought it might be the possible point zero of our creation. At the same time, I noticed that the real arguments seem to be over the existence of spontaneity. Does anyone here have an aesthetic difficulty with absolute spontaneity, not spontaneity that's just seems that way beyond our understanding of the universe?
Jim?
Absolute spontaneity sounds like something happening according to no law or no rule. Is that what you had in mind?
Yes, not dictated by external factors.
Yeah. Well, I mean, it's very problematic in what sense laws dictate events to begin with. I mean, if laws, this is my complaint about Larry, is that he sees laws as though they're divine commands.
Who's Larry?
He doesn't like being called Larry.
Yeah.
So there's some needling going on here.
Professor KRAUSS. Laws somehow reach out to events from outside space-time and control the way events occur. They cause events to occur in a certain way, and that means, of course, if laws are causing events to occur, you need another set of laws to explain how the first set of laws cause events to occur. So it gets very messy, and laws are sort of like, either they're like platonic, timeless entities that float above the space-time world, or they're like divine commands that exact obedience and prevent things from being spontaneous. I think that laws are simply high-level summaries of the patterns in the world, and that's why I don't see how you can appeal to laws to explain the existence of the world, to explain why there's something rather than nothing, because laws inhere within a world, they don't have any power to exact obedience from the world. The laws of Newtonian physics are a summary of irregularities such as the planets rotating around the sun. They don't
force the planets to revolve around the sun in certain orbits. But I mean, I feel I'm evading your question about absolute spontaneity. Is there a world in which there were no patterns and no regularities at all? Is that conceptually possible? I think not, because there results in the mathematics of combinatorics, which say that there are always going to be some regularities. You can't have a completely random world. So, yeah, I don't think you could have complete spontaneity, but that sounds like I'm talking through my hat. No.
That's why I picked on you. Yeah. Next question here. We'll just take these last set of questions and we'll call it a night. Thank you, sir. Yes.
All right. So there is a theory that the universe runs on a cycle in which it ends, and then everything shrinks back down to a really small size, and the Big Bang happens again. The Big Bang is a reaction to something, and something has to trigger that reaction. And so, does that mean that absolute nothingness can never, exist? There always has been something.
So can I?
Yeah, Eva.
I mean, that's an interesting thing that should have been brought up. There's certainly a logical possibility of maybe an oscillating universe that never quite goes away.
It always was, if it's oscillating.
If so, I mean, there are models of this which work up to a certain point, but it's challenging. I mean, it requires a certain source of stress energy to obtain the sort of crunch bang that you're asking for repeatedly. And I don't know of a realistic model of that, but it's a perfectly good question to ask.
Thank you.
Yeah, it's not.
Your question got complimented, and we have no answer for you. That's what it sounded like. Okay.
They're models, but not good models. Yeah.
Typically, when a scientist says good question, it means they don't know the answer, right? That's how that works. We'll go through these real quickly. Sir.
So this evening seems to have been focused on defining nothing, definitions of nothing, but when it came to sort of the relevance of nothing, it was sort of quick to dismiss the question of why in favor of the question of how. And I guess to me it seems that the question of how is at least directionally simpler than the question of why, insofar as we may not exactly know the answer to how, but we keep getting closer as science advances us, and we really can sort of infer a first cause at least.
Is there a question?
Yeah, because
okay.
I mean, I think the point is how is a process, and if you go from the very first something and just go one step back to nothing, you no longer have the device of saying this caused this and this caused this and this caused this, because by definition there was nothing to cause something. So I guess my question is, is the relevance, is our fascination with nothing in your views really coming back to the question of why? Why does this all exist?
Okay, so wait, so Lawrence's book begins with the word why. Tell me the title of your book.
Actually, the title is A Universe from Nothing. The subtitle is Why Is There Something Rather Than Nothing?
The subtitle begins?
Why?
Okay,
and then the preface, I explain why that's a bad question.
Okay, but let me ask you.
But
isn't it true that we had an argument about the difference between how and why, and you were discarding the why?
Well, I don't think why has any meaning. Why assumes purpose. If you really mean why, always means how, unless you assume there's some intentionality. That's the assumption of why, and then you're assuming the answer before you ask the question. So why may not just be a good question. There may be no intentionality. There may be no reason for why the universe exists. There's a process of how it exists. And then the first cause, if time doesn't exist before the Big Bang, what do you mean by cause? What do you mean by before? Those questions, which have been so vital to the way people think, may just be bad questions.
Now, the question of why asking the question why does not presume intentionality.
What do you
give
mean
you an example. Why, suppose we have the final theory, which everyone thinks is just over the horizon. Once we have that, as Steven Weinberg will tell you, or any reflective person will tell you, there still leaves open the question, why that theory? Well, one answer to that might be that it's the only logically consistent theory.
So
that's
probably
really not true, because the theory of nothing is
of
logically consistent. But so a further answer, and this was sort of toyed with by John Archibald Wheeler, who coined the term black hole, among many other achievements, was Richard Feynman's teacher. He said that the laws of physics might be the only logically consistent set that permit the emergence of conscious observers. That would be another interesting why. Once you answer the how question, how the laws of physics ordained a universe, coming out of a patch of false vacuum, then you can further ask the why question about why the laws have this general form. And I think that that's not to be discarded lightly.
I would
That's an
say that's
interesting
a question
intellectual
of
inquiry as well.
how did the laws of
See what you
physics
started
derive
here?
the form they do?
We got to move on.
Okay.
Thank you. Yes.
Well, Descartes' theory of I think, therefore I am kind of gives this idea of existence being something that we have to qualify. We have to qualify existence using some sort of description. And sort of, you were talking about how reaching behind your head in that space that we can't really see and can't really describe kind of gives a description to nothingness, but nothingness can't really be described. So how can we talk about nothingness when we can't really describe it?
You're Professor where? Yeah, I like that question.
Well, that's why I use the example, because you can't really describe what it looks like back there. So
Professor Gott's
metaphor
reference to nothing is the best answer to your question, because he didn't even describe it. He just gestured to it.
No, but look, physicists, the whole point of science is we actually say this we can describe and we can discuss it. And it may not be what you mean by nothing, but it's, so these are we try and make things well-defined, and inevitably they're mathematically well-defined. And that's the best we can do. And we can't do any better. And it may not satisfy you, but that's it.
Scientists try to answer the how question just because that's what the science can answer.
But you're leaving it a brute fact why the laws of physics take the form they do. And I think that the principle of sufficient reason, always look for an explanation. For any truth, try to find an explanation of why it's true. For anything that exists, try to find an explanation for its existence. This is a great principle that's always driven inquiry, and it's been the motor of science. And I think to discard it once you arrive at the final theory is a certain, it's intellectual philistinism, it's cowardice, it's laziness.
No, but I think it's just semantics.
See what you
I would
started?
say it's how.
Yeah, anyway. And you're all of those things, and a slut.
The last question of the evening. Sir, you better stop. Otherwise, shut them up somehow.
I just want to thank you for being here. I was on my way to Acme Auto Parts, and somebody pulled me into the here. And I don't have the foggiest idea, but I just wanted to say my thought was that in the multi-dimensional universe, or the string theory idea, I wonder how many of these forums are going on out there in the universe right now, talking about the same things. The other thing is, if this is being recorded right now, I think at least what this panel and what this process shows is the passion with which we look at these things in science and trying to find the answers of how and why. And that's at least, because if we record this, and in 25 years we all come back, and your son is the moderator tonight, and we look at everybody up here and what they've said, I wonder what they're going to be saying about, they were on target,
I doubt it, really.
I hope we're all wrong. No, I really hope we're all wrong.
The other thing about Descartes, what I really understood was, and I have reason to understand that I'm pretty accurate in this, is that, because I was over in Paris for a while back, is that his thing of je pense donc je suis, or I think therefore I am, was not the end of it. What we really don't know is I think therefore I am a something, and that was left out. So we don't really know what was after that. So.
Well, I certainly hope we're all wrong. I hope 25 years from now we've learned a lot more, and that's because we do science and
right. So I think what I'm saying is that we don't really have the answers tonight. We have the best answers that we have at this point in time.
Excellent point to end this one. Thank you all. I'd like to, just before we break, I just want to publicly thank some people who helped run this event. My executive assistant, Elizabeth Stachow, who runs my life. Laura Venner is our stage manager. Suzanne Morris runs the Hayden programs. And Dominic Davis is also active in making all this work, and a bevy of volunteers. I want to thank them publicly, and give us one last round of applause for the panel. We'll see you next year, or back at the tables where we have the book signing. You all drive safely. Thanks for coming.